Hello, everyone. It's Doug Frey again, and this is part 2 of this COMSOL Multiphysics tutorial. And in part 1, we covered some of the basic things related to COMSOL. And in this part 2, we're going to specifically address the example problem that was described in part 1, which was the entrance length in a tube, calculation of the entrance length in a tube for laminar flow. So let us go back to the COMSOL file or COMSOL model we had been making, and this is the point that we left off. A couple things I wanted to mention. Again, in this first panel, the panel on the farthest left is our node tree. If we click on the very top node, I wanted to mention that this is where you can select the unit system. We're using the SI unit system, in other words, meters, seconds, etc. If you wanted to change it, you could change it here. The name of this node is the name of the file. You might remember that used to say untitled because I hadn't saved the file and named it. Now it's called COMSOL tutorial. And one more thing I want to mention is, I believe it's under geometry. Okay, it's changing from I can't find it here. Changing from Cartesian coordinates to cylindrical coordinates. I've already lost where it is. That shows you how quickly it is you can lose things. It must be under definitions. Yeah, coordinate systems. Finally found it. We're using a Cartesian coordinate system now just for convenience. I passed up using an axisymmetric coordinate system, and that would have been a cylindrical coordinate system, and it would have assumed axisymmetric geometry. But even without assuming axisymmetric geometry, I could switch to a cylindrical coordinate system. And I didn't do that here. I could even switch to a spherical coordinate system. Obviously, cylindrical coordinate system makes sense here. But I'm going to stay with the Cartesian coordinate system because I think we'll see that it's easiest to look at things. So changing the coordinate system is under definitions if you want to change to some other type of coordinate system, even without assuming axisymmetric geometry. Okay, so just to review, you might remember we first of all defined some parameters. We also defined some variables and functions, although we're not going to really use those. But again, some of these parameters we are going to use, and we already did use them in determining the size of the cylinder. And then we selected a material. The material shows up down here. The material is water. And that came from the physical property database of COMSOL. And then we developed or defined our geometry. That's cylindrical geometry. And now we're ready to really start the meat of the model, which is to delve into the physics. And the first thing we're going to say is that we only have one domain here, domain number 1, and you can click on the domain and see it here. One domain, it's the cylinder, really. And the domain is in three-dimensional geometry would be a three-dimensional region in space and three-dimensional geometry. We could, if we wanted to, divide this up into multiple domains. But we have one domain, and we are going to say that the Navier-Stokes equation applies in this domain. And here are the equations for the Navier-Stokes equation. and possibly written in a slightly bit different format. It is steady state, so there's no temperature dependence. The first set of terms are the inertial terms. The second set of terms, or the first set of terms on the right-hand side, are the viscous set of terms. F is the body force. And the bottom equation is the continuity equation. Those are the equations that we are going to be solving. And some other choices here we don't have to worry about. There's no turbulence going on. It's incompressible. And we're essentially going to be assuming we're at 1 atmosphere pressure. Might be useful to look at the dependent variables. And we're in a Cartesian coordinate system. The velocity components are u, v, w. That's velocity in the x, y, z direction. And the pressure is going to be denoted as P. So these are the dependent variables that are going to be calculated by the Navier-Stokes equation. They're basically velocity and pressure. Okay. So far there was really nothing to change, but now we're going to go to some of the subnodes. Fluid properties. I suspect there's also nothing we have to change here. And again, this node applies to domain 1. There actually is only one domain. And let's take a look at the equations here. Again, same equations. And there is a temperature. It's a user-defined temperature, which means I can change it. And that's really the only option. I'm going to assume 293 Kelvin. I could change it by clicking on it and changing it. Notice the units are Kelvin in square brackets. And the model needs to know both the density and the viscosity. And notice it says from material. That means it's going to use the material that we define. That's going to be liquid water. We could change that to user-defined. And if we change it to user-defined, then we have to put in a density. So we might put in, say, 1,000 kilograms per cubic meter, which is the proper units in the SI system of units. But we're actually going to take that from material, same with the density. So there's really nothing we have to do here. The next is the initial values, and these are actually not going to be used because this is not a time-dependent problem. I guess they are used when you solve the problem as an initial guess, when you use Newton's method to solve the problem, but they're not critical here. They're not going to show up in the problem. If we had a time-dependent problem, then the initial conditions would be important because that defines the starting conditions for the system. But here, they're not critical. Notice they're all set at 0, which is fine. And again, their only use is going to be in Newton's method for solving the problem. You do need an initial guess, and we'll take the initial guess from that. Okay, now we're down to the next node here, which is a wall boundary condition. And notice that we have 6 boundaries here, and those are 6 regions on this cylinder. And so the 6 regions on the cylinder, let's highlight some of them. So number 1 is actually this. I'll rotate it here. Let me actually, you might remember to expand it. It's 1/4 of the circumference of this cylinder. You might wonder why the circumference is divided into 4 regions. That's a default choice. We could change that. Actually, we only need 1 region here because we're going to specify the no-slip condition. And by clicking on these, you can see which ones we want. So, 1, 2 is another boundary region on the circumference. I imagine 3 is also, unless I'm wrong, I think I am wrong. 3 is an end condition. In fact, 3 is the entrance. Should remember that. 3 is the entrance. Let's see, 4 is going to be, that's probably the other one. Yep, 3 and 4. So 4 is the outlet. That's going to be something we need to remember. Move this down here. 3 is the inlet, 4 is the outlet, and 5 and 6 are going to be more of those circumference. Okay. So we're not going to do anything here. Right now, these are all no slip. So right now, all 6 of those boundaries are the no slip condition. And we actually cannot change it. What we have to do is override it. The reason why COMSOL is constructed this way is so that even if you kind of mess things up, you will have a valid set of boundary conditions. And right now the default is a no-slip condition at all the surfaces. And if we don't do anything, we will have a very simple problem where nothing's happening in the cylinder. Not very interesting. But we cannot change that. We have to override it. And so we create nodes underneath this wall 1 node. And if a node is underneath a node, it overrides the one above it. So we've got to tell COMSOL that 3 is an inlet and 4 is an outlet. So the way I do it, again, I'm sure you could do it with these menus up here. But what I do is I right-click on the main laminar node, and then I find an inlet boundary condition. Okay, so call it inlet. Just right-click on inlet, and it created the inlet, but it doesn't know which boundary to call the inlet. Now we know it's number 3. So several ways to specify number 3. What I'm going to do is rotate until I can see number 3. So number 3 is right here. What I do is I left click on it, and that selects it and simultaneously puts it in this window. So now I've told it that boundary 3 is an inlet. There's several ways to do it, and so let me get rid of this and show you a second way. A second way is just to put all the boundaries in there and then subtract the ones you don't want. We don't want 1, 2, we do want 3, we don't want 4, we don't want 5, don't want 6, and we just check it. Yes, that's the one we do want. So 3 is an inlet. Notice we're doing an inlet boundary condition. And the equation for the inlet is that we specify, notice, the normal velocity. We specify the normal velocity. And what is that going to be? Remember, that's a parameter that we developed. We called it V inlet. You could also put a numerical number there. But we developed that parameter table exactly for this purpose, that we wouldn't be putting numbers in. And after we get this model constructed, we can then simply run it from the parameter table. Okay. So V inlet, that's the inlet. And one more thing, if we go to the wall, you'll see that we've overridden number 3. Okay, overridden number 3. That's good. And now we need an outlet. So what I do is I right-click on the laminar flow main node. So right-click on it. We need an outlet. Okay. Again, we have to tell it which of the boundaries is the outlet, and you might remember it's the one on the opposite end. So I'm going to rotate this, and the easiest way to do it is put your mouse on that boundary, right-click, and you'll notice it shows up. And so it's telling us that that outlet is surface number 4. Okay. And there's various things to do at the outlet. We are going to give it a pressure, and I think the problem says the outlet pressure is 1 atmosphere. The idea meaning it was, it exits to the atmosphere. It's so if I redefine the pressure as gauge pressure, which I'm free to do because the only thing that's relevant are pressure changes, I can actually leave the pressure here at 0, meaning it's zero gauge pressure at the outlet. I do have other options for the outlet. I can specify velocity or something, but the problem statement was that the outlet was at a fixed pressure, and in fact it's going to be zero pressure. I'll say that these pressures are gauge pressures. Okay, so that pretty much is our model. We might want to check it by going back up to wall, and notice the wall means the no slip condition at the wall. That's true for boundaries 1, 2, 5, and 6, but 3 and 4 have been overridden by nodes underneath the wall. If you look very closely, you can see these little red arrows, and they're pointing towards the wall, meaning they're overriding something in the wall. Okay, that really, unless I've missed something, is the whole model. You know, we're kind of have done the model, and the second thing I want to do then is create a mesh. So create a mesh. So click on mesh, and we can make a custom mesh if you want, but works pretty well to make the physics-controlled mesh. And what I'm going to do, for the sake of illustration, because I think this is what the students in my course are going to have to do if they're using the virtual desktop environment, is create a course mesh. So I'm going to create a course mesh here. And then I'm going to stop this video. This will be the end of part 2. Part 2 is a lot shorter than part 1. I decided part 1 was a little too long. I didn't realize how long it was. But I'm going to create this course mesh. I hope it happens pretty quickly. Oh yeah, we are going to, actually I'm not going to stop quite that quickly. So I'm going to create actually a normal mesh. Sorry about this. I'm going to create a normal mesh, then I'll actually pause the video because the mesh might take a while to create. And then we'll also then solve the problem. And that will be the end of this first video. So let's first create the mesh. I'm going to create a normal mesh. And so I just select normal. I'm just going to use a physics-controlled mesh. You'll see that it's a physics-controlled mesh is very logical. It's going to create smaller elements, finite elements near the surface, and larger finite elements towards the center. But let me now start building it. We'll just see how fast it builds it. I think it's going to take a little bit of time. But let's build the mesh. So again, under Build All, I can left-click. And though it's building the mesh pretty fast, you can see the progress in building the mesh, this little green arrow here. And it's going pretty fast. Bear with me here. It's almost done creating the mesh. Hang on here. Of course, it always stalls out at the end, but it'll get there. A couple more seconds. Just hang on. What we're going to do next is do an actual simulation. Okay, finally it did the mesh. Mesh is done. You can see it kind of filled in the mesh. It might be interesting to look at it. So I'm going to left-click on the mouse and rotate so the cylinders end on. Then right-click on the mouse and put the mouth of the cylinder kind of in the center of the field. And then I'm going to zoom in, and we can see some details of this finite element mesh. You know, it has very artistic shape, but you can see at the walls, we have a much finer grid at the walls and at the center. The whole grid is customizable, but it does a pretty good job if you just say physics-controlled mesh. If it sort of recognizes where it needs a lot of mesh points and where it doesn't. So that's okay. Well, you can see we can zoom in. Maybe we'll zoom in also on the wall. Not all that interesting. Zoom back out here. Okay, that's my mesh. That's a normal mesh. Students using the virtual desktop environment, I think you're going to have to use a coarse mesh or you're going to run out of memory. Okay, we are ready to run this thing. And what I'm going to do is just start the running and maybe show you a couple things while it's running. Now, the way I start the running is I left-click on Study, and I right-click, and then there's going to be an option called Compute, but there's actually at least two other ways to start the computation. You can start the computation by clicking on that button, and I believe there must be a button up here somewhere. Yeah, under Study, and it's got to be here somewhere. Compute, got to be up there somewhere. Can't even find it right now, but I found two other ways to start it, so I'm not going to complain. I'm kind of superstitious. I'm going to start it the way I normally start it. So start compute. So again, we start over here. I'm going to right-click on Study, and that's going to bring up all the possible subnodes. And compute is one of those subnodes. So hopefully I didn't miss anything. It'll give me an error if I miss something. I don't think I missed anything. So compute, and it's kind of preparing things now. So not going to be very exciting, but I want to, hopefully it will very quickly show some of the graphics associated with solving the problem. And it's starting to do it now. So a couple of things I want to show you first. Down here it shows the memory. And already we're using, the actual memory we're using is 1.84 gigabytes. And the virtual desktop system is only going to show you 2 gigabytes. So it's already kind of getting up there. Maybe you can barely do a normal, solving it pretty fast, actually. This green bar shows you the progress. The little red dot here is to cancel, but I actually want to show you some of these convergence plots. You can see right now we're on the 4th iteration. So basically the finite element method is reducing these partial differential equations ultimately down to a set of algebraic equations. Then it's got to solve those algebraic equations using some kind of Newton's method. You can tell by the green arrow it's almost done. It's done 5 iterations. The vertical line here is the error, or the vertical scale is the error. And you just need that error to get smaller, and it is getting smaller. It actually solved the thing. Kind of amazed it solved it that fast. I don't believe I went above 2 gigabytes. So students using the virtual desktop system, you actually may be able to solve this using a normal grid. So that's pretty good. Okay, so I've solved the problem. You're looking, maybe I'll show you just one. Well, there's some automated graphs. It tries to make graphs as best as it can, but it actually doesn't do a very good job. So I think I'm going to stop video 2 right here. We've done the calculation, but now we have to make some nice graphs. The default graphs are in the node tree underneath Study, and in the results section, we're going to do some work to make some very nice graphs. There are some default graphs, but they are really not that great. So this is the end of part 2. And part 3 will be focused on making some nice graphs. So with that, I'm going to stop sharing and stop recording. Sorry about this. Okay, I have to figure out how to stop recording. stop recording.